Okay, so this video is going to explain how the method of finite differences works and really why it works, and how we can use this delightful little tool only in the events when we just can't see or find a pattern. But I want to tell you right now, first, always when you are looking for a pattern, you try your own ideas first. Okay? And if you can't see a pattern, then you can try finite differences and other tools. Okay? So finite differences, this is a tool to try to find number patterns and then also use that to generate an explicit formula. So let's just examine a few known relationships so that we can make some observations so that you will believe that this technique works and how it works. Okay, so I'm going to, normally you're not going to be given what the function is or the explicit formula. You'll have to find that. But let's take a look at these two examples so we can kind of work backwards so you see what's going on. So the points for this particular function, if I put -2 in for x, I will get -6 plus 2 is -4. -3 plus 2 is -1. 0 plus 2 is 2. And let's see, 3 times 1 is 3 plus 2 is 5. 2 times 3 is 6 plus 2 is 8. And 3 times 3 is 9 plus 2 is 11. Okay? And notice that the x values are just consecutive numbers. -2, -1, 0, 1, 2, 3. That means that they are in a row, kind of. You could actually also take consecutive even numbers or even consecutive multiples of a 3, but they have to be equally spaced. Okay? The x values have to be equally spaced. And I'm going to generate the numbers for this second one that I know. If I put -2 in, -1/2 times -2 is 1 plus 1 is 2. I put a -1 in, -1/2 times -1 is 1/2 plus 1 is 3/2. By the way, it's always nice to work with fractions instead of mixed numbers. Put a 0 in, and 0 plus 1 is 1. Put a 1 in, -1/2 plus 1 is 1/2. Put a 2 in, -1 plus 1 is 0. Put a 3 in, -3/2 plus 1 is -1/2. And put a 4 in, and you get -2 plus 1 is -1. Okay? So now let's take a look at some of the differences. We might not see that pattern. If we were given these tables, we might not see that pattern. So we might be looking at what those differences are. So -1 minus -4. -1 minus -4 is 3. 2 minus -1 is 3. 5 minus 2 is 3. 8 minus 5 is 3. And 11 minus 8 is 3. So we might, if you're really, really savvy with mathematical functions, you're noticing, well, that's pretty obvious because there's a 3 right there, and 3 is my slope, okay, of the line, or otherwise known as the rate of change. And so, yeah, if my x's are spaced by 1, I'm going to see a rate of change of 3 in my y's, okay? 3 over 1 would be my slope, and there I see it in the equation. That makes perfect sense. So let's check this for the second equation. 3/2 minus 2 is -1/2. 1 minus 3/2 is -1/2. 1/2 minus 1 is -1/2. And so on and so on, all the way down the line, just as we would suspect, okay, because again, it's a linear form. All right, and we see that. So what we're seeing that our differences in our y terms becomes constant after one set of differences. Again, that makes sense because we're talking about lines. The definition, the very definition of a line is a function with a constant rate of change. So here I have graphed y equals 3x plus 2, and you can see I go 1 over and 3 up for each one of those points that's graphed. Okay? The line doesn't change its constant slope or constant rate of change. So there's my line with the slope of negative 1/2, down 1 over 2, down 1 over 2, right? Down 1 over 2. Okay, or in this case, down 1/2 over 1, right? Down 1/2 over 1. So constant rate of change. So it appears that when the differences become constant after one set of differences taken, we have a line. But what happens if that pattern isn't linear? Okay, if that pattern isn't linear, let's see, if we take y equals x squared, 1 minus 4 is negative 3. 0 minus 1 is negative 1. 1 minus 0 is 1. 4 minus 1 is 3. And 9 minus 4 is 5. Okay, those aren't constant differences. So let's take a look at the next set of differences. Negative 1 minus negative 3. Negative 1 minus negative 3. See, negative 1 plus 3 is 2. 1 minus negative 1 is 2. 3 minus 1 is 2. 5 minus 3 is 2. So it looks like, if the function is quadratic, it looks, this is a conjecture by the way, I'm not proven, but if it's quadratic, it looks like we have a constant difference in the second set of differences. Okay, let's just think about what that means graphically. Okay, as we look at what happens with the rates of change. So these are the points, by the way, that are graphed up there. I'll take off that graph because I'm only graphing the points. All right, so these points are down here. Negative 2, 4, right there. Negative 1, 1, 0, 0, 1, 1, 2, 4, 3, 9. So we don't see this constant rate of change happening like we did for a line, right? Okay. In fact, we see first kind of a negative, a big negative, a large magnitude negative anyway, then a lesser negative, and then 0, and then a little bit positive, and then a bigger positive, and a bigger positive. So does it seem like the rates of change are increasing by 2? So the slopes are getting bigger by 2 each time. And P.S., if you've had calculus, this should make sense. A little sidebar for the calculus people out there. The first derivative of that quadratic would be 2x, and the second derivative of that quadratic would be 2. And for quadratics, it takes 2 derivatives to settle down to a constant. Okay? So the rate of changes is constant. All right? So those are, here we're looking at tangent lines and seeing, oh yes, those tangent lines go from a strict negative to a 0 to a little bit positive to more positive to more. So those tangent lines, those slopes of those tangent lines are increasing at a rate of 2. Okay? So if it takes 2 sets of differences to reach a constant differences, the relationship appears to be what? yes, the relationship appears to be quadratic. Hopefully you were listening. What is the form for a general quadratic equation? Okay, so I'm asking y equals what? What's that general quadratic form for that equation? I hope you typed y equals ax squared plus bx plus c. Okay, or took a note on that. And what's the graph called of a quadratic function? What's the name of that graph, by the way? Well, that is a parabola. Okay, it is not a U shape. A lot of people say U-shaped. It's really got a special nature to it. It's called a parabola. Okay, so let's try now to find the function for this particular set of points. Okay, so I first look at that. I notice that all of the x's are in order. They're consecutive. I look at those values of 9 and 4, let's see, 0 to 3, and I'm trying to see if is there anything I see how to get from -1 to 4, or -2 to 9, or 0 to 3 that, might help. Is there anything I see in my own head for a pattern? Could I square it? Could I square the x's, and I'd get -2 squared is 4, and then I'd add 5 to get to 9. And then okay, so if I square the x of -1, I get 1. I wouldn't add 5 to get 4. So I'm not seeing anything, but I always give it a try first, okay? Always try your own ways first. And then I gave it a light try because I'm recording, but you might look around, poke it with a stick a couple times. So I'm going to look at the differences. 4 minus 9 is -5. 3 minus 4 is -1. 6 minus 3 is 3. 13 minus 6 is 7. 24 minus 13 is 11. And 39 minus 24 is 15. So no differences in that first set of differences. Okay, so I'm not talking about a line here. So it's not linear. Okay, because I don't see no constant differences. So then I'll check the second set. -1 minus -5. So that's -1 plus 5, that's 4. 3 minus -1 is 4. 7 minus 3 is 4. 11 minus 7 is 4. 15 minus 11 is 4. Okay, so I am thinking at this stage, I'm looking for a quadratic function. Okay. A graph can also be helpful in this. So you might take a look at graphing those points. Here's a graph of those points using Desmos. If you just go to the plus sign up there, it'll give you the options of entering a table. So this is those points hand plotted. So I stuck it in here rather than doing it live because I learned the hard way that if I switch screens using this game recorder, I lose the whole previous recording. So there you have it. Okay, so this looks like it's going to be parabolic. So that kind of confirms the idea that it's a quadratic function. So how do we then get that second set, or how do we get that quadratic? We know the second set of differences is constant. We're suspecting it's quadratic function. So now we have to determine A, B, and C for that function, right? Okay, so you do this by selecting any 3 points in your set. I've chosen kind of the easy ones. I like easy numbers to work with, so 1s and 0s are always my choice, but any 3 would work. You could choose 13, 2, or 2, 13, excuse me. All right. And you put them into that general quadratic, trying to find a, b, and c. So I'm going to put in 4 for y and then negative 1 for x. So negative 1 squared is 1, so 1a. And then negative 1 times b is negative b, and then plus c. So there's no x in there. And for the second one, 0, 3, I put in 3 for y and 0 for x. So this is really nice because I get 0x squared plus 0x plus c. So I already have a value. I have a value for c, which is really dandy. And then I put in 6 for y and 1 for x. So that gives me 6 equals 1a plus 1b plus c. So now I just have to figure out what a and b are. So I'm going to take that first equation and I'm going to put in the c value of 3. A minus b plus 3. I'm putting this in. Well, that just gives me, if I subtract 3 from both sides, 1 equals a minus b. I'm going to do the same thing down here. 6 equals a plus b plus 3. I put in that 3 value for c. And so then I subtract 3 from both sides. I get 3 equals a plus b. Now I have a wonderful set that I can just do elimination on, and I get 4 equals 2a. A is equal to 2. I had c is 3. So now any equation that you have a, b, or a, b, and c in, you can solve for what b is. I'm going to take these and put 2 in there. If I put 2 in for a, it looks like my b value would be 1. And I check it in the second equation, and that looks pretty good. So my guess for this quadratic, I don't end it there, y equals 2x squared plus bx would be 1x, or just x, plus 3. So that is what I think is the quadratic equation that models these points. Now, like a good problem solver, I don't just move on. I actually look back and I check it. And instead of plugging each one of those points in, I mean, you could take each one of those points and plug it in and go, if I put 1 in for x, I get 2 times 1 plus 1, yeah, 3 plus 3 is 6. And you don't just check one point. I'm going to check all of them really fast by putting them into Desmos. Notice I just type the equation in, and I can see that that parabola runs right through each one of those points. I would look closely enough to make sure that it actually does. Okay? So that's a nice, quicker check than plugging each point in manually. But you should probably do a little mental check and check a few of them anyway. So now you try getting your equation for that one. I'm going to have you pause and take a moment and try to get the equation. You can do y equals something in terms of x. And remember, this could also have been given to you like a sequence, since these terms could be n, like the first term, the second term, the third term, the fourth term, the fifth term. So we could be looking at this in a horizontal sequence type of fashion also. So take a moment and see if you can't get the equation for that. Okay, so I'm hoping that you saw that these had these differences. Again, they were a common difference of 2, but after the second subdifference. So you are looking, again, at a quadratic, right? And hopefully after some elimination or after some substitution or whatever way that you solve your system, and by the way, there are system solvers, you can double check and use Wolfram Alpha when you don't have your own way of solving. You can check Wolfram Alpha and plug in your equations. Okay, after you solve this, I'm hoping that you got y equals, whoops, x squared plus x. And that you look back. This one's easy enough to check, so do check it and go, okay, let's take a pen here. 1 squared plus 1 is 2. 2 squared, 4 plus 2 is 6. 3 squared, 9 plus 3 is 12. 4 squared, 16 plus 4 is 20. 5 squared, okay. Maybe you didn't even use those systems of equations. Maybe you saw that pattern. Who knows? That would be really great. But you have a tool, finite differences, if you don't see that pattern when it's a polynomial. And this method, again, only works if the relationship is a polynomial. Okay, and a polynomial, again, I have it on the next slide, but I'll say it here, y equals this form. Okay, and the reason I'm using subscripts is because technically we could have a polynomial that has a degree greater than the number of letters I have in the alphabet. Okay, we only use a, b, and c for quadratics because we have a coefficient on the x squared, a coefficient on the x, and a constant term. So we only use a, b, and x for that. For a linear, we would use just ax plus b. Or we could use a sub 1x plus a sub 0, right? For quadratics, we could use a sub 2x squared plus a sub 1x plus a sub 0. It gets a little cluttered though, so that's why the preferable form is a squared plus bx plus c. So we just use those. But a polynomial is this form, okay, where you have x's with exponents, okay? Not to be confused with exponential functions, where the x is in the exponent. Okay. So I'm going to ask you to take a look at this one and say, what relationship, specifically, what type of function do you think is modeled with this? Okay. Now, what do you think is modeled with that? Take a guess. You can either type in the equation or you can type in a name if you know names of functions. What type of function do you think that is? What type of function do you think the previous one is? You could answer an equation or you can answer a name. Okay, so we'll call this one A and this one B. So that first one, if you looked at your differences, you would see that it took 3 sets of differences to come down to a constant. So that is actually a cubic polynomial. Okay, I'm not asking you to find it, but it's a cubic polynomial. We could find it. We'd have to write, 4 equations? We'd have to take 4 of those points and plug them in because we have 4 unknowns. At that stage, I'd probably try to find some tool or technology tool that would help me solve a system of linear equations. This one, in the red letter B, I guess we called it. That was A, and this is B. That one does not settle down, okay? This would continue to go on and on, okay? You would not, you should be sensing that you're never going to get a constant set of differences. So this bad boy, if you thought about what happens graphically, too, and I hope you did, -2 is at 1, -1 is at 2, 0 is at 4. You should see a little bit of a pattern going on here, and then the next one is at 8. Each time it's doubling, okay? So it gets steeper and steeper and steeper and steeper. This is an exponential function, right? And it's base 2. Okay, it's 2 to some power. Okay, and if we look at it, 2 to the -2 plus something maybe is 1. So I'm saying 2 to the -2 plus 2 would be 1. Let's see if that idea works in the next one. 2 to the -1 plus 2. Does that equal 2 for the second one? So I'm putting in x in the circled parts and y in the squared parts, I guess. There. And it seems that that's working, so my guess at this function would be 2 to the n plus 2. Or since I used y and x, I guess I'll say y equals 2 to the x plus 2. Okay, so that's an exponential function. But don't forget, you can use graphs to give you a hint at that kind of thing. Okay? Next page. So take a moment and try getting a formula for that lovely thing. Did you use your gut? First, if you check those differences, they don't settle down, and if you get down to only having one difference, guess what? You cannot make a conclusion from one difference. All right, that's not a constant. So look at your gut, see if you see something. I happen to see 2 in the denominator each time, and I see powers of 3 happening in the numerator. Okay, powers of 3. So that function was 1/2 times 3 to the x. Okay, if you really looked. So, you want to see if you see something first. Okay? So, always try to see the pattern first, using your own intuition and common sense. Use finite differences only when it's unclear what the pattern is and you require a tool to help. Okay? So, identify for these. We'll call this one A, and this one B, and this one C. Just identify what type of pattern is it. Is it linear, quadratic? Is it exponential? Might it be cubic? Just type the word in for each one. A, B, and C. You don't have to find it, because I'm thinking you could make a set of equations and solve those simultaneous equations. So I'm hoping you got the first one. You said hopefully quadratic, because it would take 2 sets of differences. The next one, since it's only one set of differences, hopefully you said it was linear. And then again, quadratic. Okay? By the way, when you recognize that it's linear, you can write y equals ax plus b and substitute 2 points in solving for them. It doesn't matter which 2 points. I'll take 1, 1, and 2, 3. So I'll put 2 in for x, 3 in for y, and you can take that, just solve that system, right? By putting those 2 points into a line form. Okay, and that's how you can get that if you don't see the pattern yourself, once you know it's linear. And this one, the last one, again, you should have seen a set, let's see, 4, 6, 8, 10. You should have seen a set of differences of 2 after the second set of differences. So running through this one more time, before I ask you to enter your final conclusions on 2 last problems without me telling you the answers, okay? If you're given consecutive terms like this, either in a sequence form or in XY table form, if you're given 1, 2, 3, 4, 5, 6, or 0, 1, 2, 3, or -1, negative 2, -1, 0, 1, 2, etc. If you're given consecutive terms, look for differences in the terms. If it's constant, you have a linear pattern. So you have something like this, ax plus b, okay? And then you just determine a and b by putting points in. So you can put 1, 2 in and 2, 5 in, get a system, okay? And you can solve it any way you want to. Substitution, elimination, whoops. Okay, if the difference between the terms is not constant, you can check the differences between the differences and see if it's constant. For example, this one. Okay, so you look at those differences, 1, 2, 3, 4, and you'll see a difference of 1 there. So then you take the quadratic and you put in some points that you know, right? I'll cover that noisy stuff up down there for a minute. Okay, so you put in 0, 1, 1, 2, and 2, 4. You get 3 equations. Oh, I guess I have a third one there. I don't know why. All right. If you have a system, you only need one of those equations, or excuse me, 3 of those equations. So you can use these 3, I think are the easiest ones to use. But if you don't have that 0 term, I guess I wanted to model one where you didn't have a 0 term. I took those bottom 3 equations. Again, if you have that 0 term, you're given that c is 1. So I modeled solving a system of 3 equations where you weren't given that easy point. So I took those 3 equations and I did repeated elimination. So those bottom 3 equations down here, I multiplied the top equation by -2 and then eliminated. Then I took the bottom 2 equations, I multiplied that bottom equation by -1 and eliminated. Then I took those 2 in a and b and eliminated those, the b over there, and got a, and then I went backwards and solved for a, b, and c. Okay? How else can you check? Hopefully you thought about making a graph. So you could take those points, you could plot them and run that the function through it. Then the function is, and I didn't write it, and I should have written it, the function would be a sub n is equal to, what was a here? 1/2 n squared plus b was 1/2 n plus 1. Okay? So that is the function. So we could plot those points and then see if that ran right through it. So now you have 2 problems to do. Here's your first one. Copy those and see if you can write me an explicit formula for the nth term. You can do it any way you want. I would suggest trying finite differences because this is a video on finite differences. So take a moment, work that problem out. Okay, well, hopefully you entered your response for that one. Hopefully you saw what type it was first, solved a system of equations. Here is your next one and your last one. So enter an explicit formula for a sub n in this case. So this is n, the term number is always n, and the term is a sub n. Okay? And check it. Okay, so this is the end of finite differences. So hopefully you now have a new tool for writing an explicit form for polynomial patterns that you cannot see intuitively. See you in class.